मेरे लेक्चर का विषय है ओवरव्यू ऑफ प्लानिंग डिजाइन एंड कंस्ट्रक्शन ऑफ ब्रिजेस। ब्रिज होता क्या है? बाय डेफिनेशन, एनी स्ट्रक्चर टू क्रॉस ओवर एन ऑब्स्ट्रक्शन लाइक रिवर, कैनाल, रेलवे लाइन, और नीचे कोई रोड जा रही है उसको क्रॉस करना है हमें। इट कैरीज ए रोडवे और रेल अक्रॉस द नेचुरल और आर्टिफिशियल ऑब्स्टेकल्स and it is very essential to free flow of transport from one end to another end of any that obstacle, and it is a vital link in the transportation system. Without this, very difficult to cross the obstacle. Bridge controls the overall capacity of the transport system. If bridge is narrow, so we can handle more traffic. If the width of the bridge is insufficient to carry the number of lanes required to handle the traffic volume, the bridge will be constrained to the flow of traffic. If the bridge is deficient and unable to carry heavy truck loads, then load limits will be required to be imposed and traffic needs to be rerouted or diverted. Bridges are very expensive in comparison to road network approaches. As the bridge is a very key element in the transport system, a balance must be made between handling future traffic as well as the present needs and the cost of heavier and wider bridge structures to be optimized. If any bridge fails, the whole transport network in that area fails. The importance of bridge can be realized by considering a comparison between the two main components of the highway, that is road and bridge itself, which some of the pictures I have shown here. That if some bridge fails, so what happens? Bridges are very old, maybe more than 2000 years or more than that. Earlier we used to use wooden planks or stones, slabs to cross over a canal, or not canal, a river or nala you can say. Then Roman arch bridges were constructed sometimes in 100 BC. Arch bridges in China were constructed after in 700 AD. Cast iron bridge 1800 AD, wrought iron bridges 1850 AD, suspension bridge 1920. Then we come for the cavister bridge, PSC gutter bridges, integral bridges, extra dose bridges, and so on. Bridge can be classified based on materials, uses, span, structural element, structural forms, supports, and geometry of that bridge. Metals may be timber, stone, concrete, steel, composite, FRP. By uses, it may be pedestrian bridge, highway bridge, railway bridge, or carrying a pipeline. Span-wise, small bridge, minor bridge, major bridge, long bridges. You might be knowing the difference between all these. Depending on span, up to 6 meters it is a culvert, 6 to 60 meters is a minor bridge, and more than 60 meters long span is major bridge. Minor bridge having a total length between 6 and 60 meters, and for the rural roads, the difference is different between 6 meters and 30 meters, and individual span should not be more than 10 meters. And major bridge is having total length more than 60 meters. This is a balanced cantilever bridge or Ganga bridge at Varanasi. They were constructed sometimes in 90s. What is the criteria for selection of bridge type? Geometric condition of site, subsoil conditions, what is our requirement, functional requirement, and what technology we are going to use for construction and erection, and it should be easy to maintain. What are the regulatory issues? Aesthetics also plays a very important role, and finally the economics. What are the major bridge components? These are superstructure, you might be knowing about it. Substructures include pier cap, then foundations. Foundation may be pile foundation, well foundation, open foundation, different type of foundation may be there. We can construct either a culvert or a bridge at the same location, depends on the amount of water flowing that particular location, and functional requirement to minimize the cost of construction. Planning of bridge construction. Why we need a bridge? It may be replacement of old bridge which is not functional, or unable to take the carry the design loads, or we have constructed new roads or bypass of city or widening of existing road. In that case, in all these cases, we need a new bridge. Mr. J. Goel will be informing the next lecture about details of these planning and project preparation stages, feasibility studies, planning preliminary reports, feasibility studies. We have to check the various options what available for type of bridge and span details and compare the various options from technical economic consideration and then recommendation for the suitable option. And based on that, finally accepted option, finally GAD for that option, rough cost of estimated cost of that one, preliminary economic and financial analysis and determination of viability, special design requirements, model studies if required, and schedule of pre-construction activities needs to be specified. In DPR, detailed survey and investigation along the appropriate site and alignment should be carried out. Detailed design and drawings shall then be made, and from these details and design and drawings, we have to estimate the cost of bridge. Then we have to take the revised economic and financial sanctions, and we have to prepare the bid documents, including BOQ and technical specifications, and we have to award the work. What data is needed for the planning of bridge? Index map, site plan, contour survey plan, topographic and catchment area map, traffic data including pedestrian traffic likely to use the bridge, hydraulic data. Mr. Gherwa will cover all details. I'll skip this. Soil and subsoil data. As per RE 78, we need to know the soil characteristics and erodibility of bed and banks, foundation investigation by boring and soil test to ascertain data on safe bearing capacity and settlements values, surface and subsurface soil investigation for approaches, environmental consideration, quality of air, water and ground soil, severity of environment with respect to corrosion, wind and seismic data. Details of existing utilities in the urban area is very important, and we need to find the location so that they can be shifted. Data on the existing bridges upstream as well as downstreams. We need to know what is the length and span of details of the existing bridges, what is the vertical clearance, type of substructures, superstructures, type of foundation and protection works, and special features of that bridge if any. Square screw crossing with angle of skew needs to be defined. Define banks and spread of water at HFL and high tide level, proximity of existing bridge, requirement of bank protection, alignment and length of approaches, access to the site, environmental consideration and seismic effects. After getting all these data, we have to design for HFL, OFL, whatever the case be. We have to estimate the design discharge and velocity of flow, scour depth needs to be computed, and horizontal vertical clearance and freeboard needs to be finalized. Subsoil data for foundation design and flow protection works needs to be defined. What should be considered for span arrangement? What should be the span of that bridge? PS to be preferably in line with the existing bridge in PS in case of possibility to avoid concentration of flow and substructures and turbulence. Span length based on safe bearing capacity of foundation strata, cost of superstructure vis-a-vis foundation substructures needs to be assessed, and ease and time of construction, design efforts and time required, availability of suitable materials and special agency in that particular area where bridge needs to be constructed, and easy repairs and replaceability of bearings and superstructures, and riding quality with respect to expansion joints. There are some guidelines if depend on the span length. If length is span length less than 6 meters, then we have to go for culverts. 6 meters, between 6 meters to 10 meters, we can go for solid RCC slabs. 10 meters to 20 meters span, then precast or pre-tension or post-tension beams, RCC beams. If span length between 20 to 25 meters, we can use the RCC word slab. If span length is 25 to 30 meters, then we can go for PSC worded slab. If length is between 30 to 35, RCC box, 35 to 40, PSC beams, 40 to 55 meters, PSC box, 55 meter to 120 meters, cantilever or segmental construction, 120 meters up to 1 kilometer, cable stayed bridges, 800 meter to 2 kilometer bridge, suspension bridge, like this, these are guidelines. Type of substructure may be solid wall type pier, circular column type pier, solid wall type abutments, spill through columns type abutment, straight spread return walls on independent footings. Foundation may be shallow open foundation, raft foundation, box type bridges, circular well, dumb well, double D shaped well, pile foundation, etc. Pile foundations are traditionally these are adapted for flyovers and creek bridges where no scour is expected, and span range is not more than 50 meters. Span of that span. Scour depth is between 10 meters and 15 meters only. Settlement of a foundation is not an issue, and discharge per meter length is low in case of river bridges. We can also use the piles, and for flyover creeks. For river bridges, if condition 1 to 4 is satisfied, then we can use piles also. How in urban areas, the piles are preferred due to faster construction, presence of underground services, lack of working space, and reduced nuisance due to removal of mucks, etc. Deck की width कितनी होनी चाहिए? Minimum 2 lane. Multi-lane bridges with medium verge and divided carriageways. Width between the outermost face of railing curb to be normally same as the formation width in the immediate approaches. Footpath width minimum 1.5 meter and at the same level as deck separated by the curb. Width of median verge depending on the design width of carriageway on the bridge. Crash barrier or railings in combination with the crash barrier for major bridges, flyover, ROBs are must from the safety point of view, and cross slab in the decks and footpath for the draining of the water, runway of water. As per more specifications, wearing concrete wearing code of 73 mm is recommended, but this is in our view, in CRI view, this should not be used due to problem of cracking and replacement. Alternatively, we can use the bituminous concrete 50 mm thick in single layer, or bituminous concrete 40 mm thick overlaid with 20 mm thick mastic asphalt, or stone mastic asphalt 50 mm thick in single layer, or 50 mm thick mastic asphalt layer in single layer as a wearing coat over the bridge. IRC SP 69 2011 gives the expansion joints. There will be different type of expansion joints are given that code. Filler joint with copper plate and 20 mm thick pre-molded joint filler and sealants for small gaps. Compression seal expansion joints for up to 40 mm gap. Reinforced elastomeric slab slip joint, single strip seal joint, modular strip seal joints, asphaltic plugs joint. Mr. Gherwa will be covering all these in details. Bearings may be metallic rock bearings or rocker cum roller bearings, elastomeric bearings, pot cum PTFE bearings, guided pin bearing, spiral bearings. All these will be covered by Mr. Gherwa in detail. Appendency, crash barrier, upper slab, drain spouts, and V-poles, they are very important. Detailed design and drawings need to be prepared. This includes general element drawing, detailed drawing and drawing should be based on the relevant IRC codes and international codes if those guidelines are not available in the IRC codes, and review of design based on site conditions during execution, particularly for the foundation. Sometimes we have taken the design as per the SBC at that area, but due to the construction, there may be some unforeseen changes in the particular location. Then we need to prepare the bid documents, general and special condition of contract as standard bid document of authority in case of EPC projects on lump sum basis, and model consent agreements for DBF 40 projects. Technical specification needs to be prepared based on mod specifications, and BOQ needs to be finalized, contract drawings for the EPC projects. The important aspects of project preparation, subsoil investigation very important. For DNF pile foundation, initial load test shall be carried out. Conceptual and special to implementation, step-by-step approach should be defined. Availability of land, personal materials, labor accommodation, etc. for major projects is essential. Drainage, ventilation, lighting for subways, underpasses are very important from safety point of view. Safety of adjoining structures and pedestrian movement during construction of urban flyovers, and design life of bridges 100 years as per our RC code. Then we should design accordingly so that with the minimum maintenance they can serve for 100 years. Dynamic analysis and wind tunnels testing for cable study of suspension bridges, competitive designs for speedy and accurate analysis, realistic construction programs so that we can avoid any spillway of the time run, traffic management during construction, special consideration for bridges in hilly areas needs to be given. Utility in access needs to be shifted. Node line should be contact with the bridge components. Telephone and electrical cables to be taken in ducts supported by bracket cantilever from deck and footpath ends. Maintenance walkway platform around the pier should be there. This maintenance walkway platform presently exists in the railway, not in the highway bridges, but this should be provided in highway bridges also for the future inspection ease of that. Continuous cantilever walkway at soffit level on either side of box girders should be there. From durability point of view, do not use too much cylinder cross sections, increase cover to RCC, PSC cables, control of cracking and crack width by good detailing of reinforcement, reduction in number of expansion joints and use of leak-proof joints, waterproofing of decks. We are doing some research in CRI on this topic, waterproofing of the base deck, anti-corrosive treatment to all steel reinforcement, good dense concrete with low water cement ratio. These are some of the measures for the increased durability. What are the loads for which bridge needs to be designed? Permanent loads, which include dead load and load induced due to creep and sinkage. And transient loads, there is a traffic load, that is live load given IRC 6, environmental loads, construction loads, etc. Design philosophy, there are two approaches, working step method and limit state method. But in the recent code on IRC 112, this working stress method has been not recommended, has been withdrawn. That code has been withdrawn, and only a limit state approach needs to be followed. I will skip this. Why this limit state method of design has been introduced in the code? Loads acting on bridges and resistance of components are random in nature. Working state method does not account the variability of loads acting on a structure and strength of its component, and limit state design approach was introduced in 1970s for design of other type of structures, concrete structures. They have two type of limit states, ultimate limit state and serviceability limit state. Ultimate limit state is related to capacity of structural components in flexure, shear, torsion and stability, while the serviceability limit state relates to stress, cracking, deflection, fatigue, vibration and associated deterioration, etc. These are some of IRC codes which are used for design of bridges. IRC 5 includes the general design features. IRC 6 loads and stresses. IRC 112 code of practice of concrete road bridges for design. IRC 22 design criteria for composite construction. IRC 24 design criteria for steel bridges. 78 foundation and substructures. 83 bearings. There are some guidelines also. IRC SP 64 guidelines for the analysis design of casting place body slab superstructures. SP 65 guidelines for design and construction of segmental bridges. SP 66 guidelines for design of continuous bridges. All the topics, some guidelines are there given by the IRC. SP 61 guidelines for use of external and bonded precision cables in bridge structures. SP 69 guidelines for and specification for expansion joints. SP 70 guidelines for the use of high performance concrete in bridges. IRC 71 guidelines for design construction of pre-tension girder bridges. For quality control also, the guidelines are given in the code. IRC SP 54, SP 47, and it should be followed. Guidelines for the design of small bridges and culverts are given in IRC SP 13, and specification of rural roads, Ministry of Rural Roads, IRC SP 22 shall be followed for the rural roads and bridges. Now, there are some for the photographs of the recent techniques which are used for the bridge construction. Balance cantilever technique, in which we start from the pier, and from that end one by one we increase the section on both sides one by one. balancing it. The superstructure bridge is built from one or more piers by means of formwork carries with the cantilever method. The structure advanced from a short stub on top of pier symmetrically in segments of about 3 to 5 meter length, and this method is applicable suitable for medium and long span concrete bridges, and it is recommended especially where steel folding is difficult or impossible to erect, as for example over deep valleys, wide rivers, traffic yards, or in case of expensive foundations condition. Another method is incremental launching of bridge construction. The sections are cast continuously one after another and then are stressed together. The superstructure growing sections by section is launched over temporary sliding bearings on the piers until the bridge is completed. 15 meter, 30 meter long sections of the bridge superstructures in a stationary formwork is cast beyond the embankment and is then pushed completely forward. And this method is applicable, suitable for the construction of continuous post-tension multi-span bridges. The limitation of this method is span should not exceed 60 meters and the bridge section must be constant. There should not variation in the sections. Superstructure of bridge has to be continuous over the whole length and straight and have a constant curvature in plan and elevation. Another method of construction which is presently used is launching truss bridge construction. The launching girder itself is normally a steel structure with rather sophisticated equipment moving forward on the bridge piers span by span. This can be suitable for multi-span bridges over difficult terrain or water where scaffolding are expensive and not feasible at all. And it is highly adaptable for a wide range of spans and type of superstructures, and it can handle casting placed concrete as well as prefabricated elements. They are most often used for placing prefab segments, match cast, and assets together or complete unit spanning from pier to pier. Now the case study of Delhi, what they have done in the past few years. You see, this is a map of Delhi, which borders UP on one side and Haryana on the other side. Initially, the way back ring roads were planned around Delhi, inner ring road, outer ring roads, and extensive that it covers a 25% geographical area is a roadway in Delhi. Before 1982 games, Asian Games, there were 2-lane bridge at Vijayabad, which was constructed in 1968, and 4-lane bridge at ITO, which was constructed in 1970, and 4-lane bridge at Nizamuddin constructed in 1970. There are only 3 bridges, but presently we have more than 10 bridges over River Yamuna to cross from one end to another end. New bridge was constructed at ISBT, which was cast in situ, precast, pre-stressed box girder bridge having carved girders. Hanuman Setu was constructed, Vishweswara Setu near Okla was constructed. 4 flyovers constructed for the Asian Games, all were cast in situ construction, and they were constructed for the traffic congestion, to ease the traffic congestion during construction. Shifting of utilities was the issue at the time, and construction time was only 18 months. Asian Village in Hoj Khas to Jawahar Nehru Stadium near Lodi Road and Indira Gandhi Stadium near ITO were the areas where we need flyovers. Flyover with precast, pre-pressed girder, PSC girders and continuous spans were constructed. In 1990s, expansion of 4-lane bridge at ITO and Nizamuddin to 8 lanes were done. Cover leaf were added to ITO flyover, use of warded slab technology. For the first time it was used in that flyover. Inner ring road was selected for improvement of transport corridor for more than 1 lakh PCU per day was there in 2000. So several great steps were planned on the ring roads at the time, and different intersections were done. In 2001, use of precast, pre-tension beams for flyovers or ramps, central span using cast in situ pre-stressed box girder were done. Then switch over to precast segmented construction due to space constraint, and Ariwal technology was adopted for the embankments in Delhi. Flyover at Moti Bagh, Africa Avenue, Nehru Place, Service Tema, Britain Chowk were constructed. Precast solid box segment was used in the road flyovers for first time in Delhi. Then low bedded trailer for transport of a precast segments of 32 tons were first time used. Testing of launching truss. Low bedded trailer carrying 100 ton capacity was later on used by Gammon. Precast segments were cast in the casting yard. Why Delhi has gone to precast bridges? For the accelerated bridge construction, for better quality control in the yard, elements with difficult shapes and congestion reinforcement can be handled at ground level in better way. Reduction is noise and dust pollution at the site, no requirement for staging at the site, minimum disruption for traffic during construction. These are some of the benefits of the precast construction. Cost saving in the large bridge projects with standardized elements and low life cycle cost. Then the steel concrete composition construction also took place in Delhi. Several flyovers constructed with the steel girders and RCC decks. Multi-level grid separator was also जो पहले मैं जो काम नहीं हुआ ट्रैफिक बढ़ता गया एक के ऊपर एक फ्लाईओवर बनाया गया फिर मल्टी लेवल फ्लाईओवर्स ग्रिड सेपरेटर्स different areas in Delhi constructed. You see the huge traffic going on. Dola Kuan grid separator was constructed. Long flyovers, 2 km, 3 km, 4 km length, long flyovers were constructed. Underpass, construction underpass was also done in 2000 at several locations in Delhi. Precast RE wall was first time used in different locations. Elevated corridor or Barapula during Commonwealth game. It's the longest, and this was planned for all type of vehicles, but after seeing the condition, it was restricted only for the light vehicles only. And that too, presently there is a huge congestion on this Barapula Nala elevated corridor. The peak hours, there are some details of this flyover, elevated 4.5 km long, where construction of 2 separate structures for up and down traffic, and precast segmental construction, which are completed in 20 months. Obligatory span of 85 meters using balanced continuity construction, sharp curve, skew spans, alignment modified to avoid the relocation of underground or overhead utilities. Deck level raised to 20 meters at one location to provide uninterrupted view of monument. That is the monument we JSA want that it should be visible from all the angles. Longest span the same Barapula, Nala, and this foot overbridge near Jawaharlal Stadium was constructed for the Commonwealth Games. Flyover with steel girders and precast RC decks panels in Delhi. First time it was tried, but it has some problem nowadays. This is a precast deck panel of that bridge. And after 2010 until date, elevated roads corridor along outer ring roads 4.3 km long, connecting between Vikaspur to Mirabag, 2.6 km long, Mangolpur to Madhuban Chowk, 2.6 km Madhuban Chowk to Mukarba Chowk. All these were done. This was in this particular bridge. It was having only a single pier at central verge with wings on the both sides for complete two-way, three-lane carriageway to range the speed of construction. And then the conversion of landfill areas to green belt that was also done in Delhi. So these are before the conversion, these are after conversion. There is a lot of sea changes there. And technical advancement in the bridge construction. We have moved from cast in situ to precast construction, shorter span to larger spans, simply supported spans to continuous spans, elastomeric bearings to pod-com PTFE or specific bearings, buried sliding plate section joints to single strip joints or model spectrum joints we have gone. Normal concrete, we have to go to high strength or high performance concrete. Quality assurance during construction has improved, and strength be designed to the durability design is the need of the hour. Other important developments are we have gone from RCC retaining walls to cast in situ RE walls and then to precast RE wall. We have started using the noise barrier over the bridge. We have also started traffic management during construction to avoid the difficulty to the traffic. Safety during construction has improved further a lot, and proper planning for shifting utilities has been done, protection of drains from contamination, etc. That's all from my side, in short. If you have any query.